The problem statement from GATE Physics 2018 reads as follows. A spaceship is traveling with a velocity of 0.7 c away from a space station. The spaceship ejects a probe with a velocity 0.59 c opposite to its own velocity. A person in the space station would see the probe moving at a speed xc, where the value of x is. This is a numerical answer type question, and we need to find the value of x and then round it off to 3 decimal places. Before we try and to solve this problem, let's have a quick look at some relevant concepts. So on the left you have the frame S, we can call it the rest frame. On the right you have the moving frame, the S prime frame, and this V is a constant. This frame is moving at a constant velocity v with respect to the our rest frame. And let's assume now, so what we know is that, let's say there is some particle here, some particle p prime, which is moving at some velocity ux prime in this frame. Note everything is primed for the S prime frame. So we know this velocity, but we are interested in finding the velocity for the same particle p. What is the velocity here? So what is the velocity of ux here? So we are interested in finding this entity. So how do we find ux from ux prime? So we can write ux as delta x over delta t, and if we obtain delta x, we already know delta x prime, delta t prime, we know everything about this frame. So how to obtain now delta x and delta t from the prime entities? We use what is known as the inverse Lorentz transformation. Note on the right side you have the primed entities, these are known entities. On the left you have unknown entities, which is t and x, unprimed ones. So I can simply find out delta x, which is x2 minus x1, using this formula. You put in the values. Similarly delta t, t2 minus t1, you put in these values, and then we reduce, put the limit that delta x and delta t go to 0 to convert into a differential. And so dx and dt come like this, and we know ux is equal to dx over dt. So we put dx, the value of dx and dt over here, gamma gets cancelled, and we rearrange some terms, and we get this formula in the blue rectangle on the left side. I just reiterate that ux prime is the speed of the particle p in frame S prime, in moving frame. V is the velocity of the moving frame itself. Ux is the velocity of the same particle when observed from the rest frame or the S frame in this case. So these are the definitions of ux prime, ux and v. So please keep that in mind. Now we come back to our problem. Before we go ahead jumping to solve the problem, we just do some pre-checks. So let's draw a couple of frames. So first frame is of a spaceship, right? And the second frame is of a space station. So there are two entities here. So this is a space station. So what we'll assume, that space station is at rest. Okay, and there's a spaceship. So from this space station we'll observe this spaceship moving away from it, and this is the frame of a spaceship on the right, which we call as S prime. Okay, so this is moving at some constant velocity 0.7 c. So this velocity v will be 0.7 c. Now what's happening is that this spaceship is ejecting a probe. So there is a probe p here, which is being ejected opposite to the velocity of the spaceship. So probe p is being ejected in this direction, opposite. So again I denoted by p prime, and let's say this velocity is ux prime, because we are in the S prime frame. Note this is S prime, is this frame of the spaceship. So again the observer sitting here, right, in space station, the person sitting in space station, the observer O here, will observe this probe. So this will observe this probe p, and let's say the velocity of this probe p is ux. Okay, so ux, or you can say that or alternately we can say that this is in this direction itself, and that it's minus 0.59 c, where this is the positive x-axis. So similarly this particle p will be observing it at moving at ux in this direction. Let's get back to the problem. No. So let's get back to the problem, and before we solve the problem, let's do a few pre-checks. So we draw the system first. So there is a system, we draw a system using like this. So there is a space station. So we draw my space station over here, and we call this the frame S. We assume space station is at rest. Similarly, there is another frame of spaceship which is moving. We know that spaceship is moving at 0.7 c. So this is my spaceship in rectangle which is moving in this direction, let's say 0.7 c, and this is the spaceship frame. So the velocity here would be 0.7 c, because spaceship will, and this is the velocity of the spaceship. And we note that the spaceship ejects a probe. So there is a probe here which is being ejected. We call this probe p prime, and its velocity would be ux prime. Why? Because it says that probe is velocity 0.59 c opposite to its own velocity. So this spaceship is ejecting a probe p prime, and it's measuring its velocity to be 0.59 c. Since it's opposite direction, we add a minus sign, and we are taking this to be the positive x-axis. So again, I repeat, this spaceship is ejecting a probe p prime, which we see here. So person observe its velocity as 0.59 c. So I am denoting in the ux. The prime denotes that we are, this observation was made in the frame s prime. Negative sign denotes this in the opposite direction, right? So similarly, a person sitting here, you see a person is space station. So this person will also observe that probe has been ejected. So we'll assume that this person observes this probe p has been ejected, and this person sitting here, the observer O, measured its velocity to be ux, right, which is xc, and we need to find the value of x. Now we check whether frames are inertial or not. So we have assumed space station to be at rest. So so station frame is inertial. Station frame of reference is inertial. What about the second frame, spaceship frame? Spaceship is moving at constant velocity. So again, ship frame of reference is also inertial. Now both the frames are inertial, so we can directly apply the Lorentz formula, velocity transformation. Those formula can be applied. Now moving frame, which is the s prime frame or the spaceship frame, what's its speed? Its speed is 0.7 c. So we write v equal to 0.7 c. What is the direction? I am assuming this to be positive x direction, so let's say it's I cap. What about number of dimensions? The question is silent about number of dimensions, but we can simply generalize to be only one dimensional problem, because there's no mention of the second or third dimension. So I assume it to be one dimensional picture, and in this case I'm assuming that dimension to be the x dimension. Now I have reproduced the system here itself. So on the left you have, so first the red rectangle denotes spaceship, while the green circle denotes the probe. So on the left you can see the space station in blue, and it observes that a spaceship is moving towards right at 0.7 c, and the probe velocity has ux. So similarly, the same will be visible here in the s prime frame, the spaceship frame on your right. So spaceship itself will appear to be at rest. This means spaceship velocity is 0, which makes sense because we are in the spaceship frame, while the probe's velocity we can observe as the ux prime. So we are given the velocity of probe with respect to ship, that is ux prime. Again reiterate, prime means velocity of probe with respect to ship, which is given as minus 0.59 c, and we are required to find the velocity of probe with respect to space station, that is the entity ux. The way we are denoting it as, there is no prime here, so velocity ux in the x direction and within the space station frame. So if we know ux prime and we want to find ux, we can apply the inverse velocity transformation, which is given by this formula, which we saw a couple of slides back. So I'll simply plug in the values. So ux prime would be minus 0.59 c plus the value of v is 0.7 c, you can note it here, plus 0.7 c divided by 1 plus the value of ux prime is minus 0.59 c into 0.7 c over c squared. So these terms gets cancelled. In the numerator you will get 0.11 c. However, in the denominator what we will get is 1 minus 0.7 times 0.59, right? So we just now need to multiply 0.7 with 0.59 and then we'll get our answer. So let me get my calculator and do that for you. So it's 0.7 times 0.59. that comes out to be 0.413. So this is coming out to be 0.11 c over point, sorry, that's 1 minus 0.413. So this will come out to be, the denominator will come out to be now 0.11 c, numerator remains the same, denominator comes out to be 0.587. Now I can do simply 0.11 divided by 0.587. This will come out to be 0.187 c. So we have obtained the velocity ux as 0.187 c. So I obtained ux as 0.187 c, and this is equal to xc. Note, velocity, person in space station, see the probe moving. This means velocity of probe with respect to space station. This is given as xc. C and c get cancelled. I get x as 0.187. So it's up to 3 decimal places itself, so I can write it as 0.187. So that's our answer. Thank you for listening.